Hello everyone, welcome to Organic Chemistry 1. This is the second part of Alkynes chapters. We'll be looking at reaction of alkynes. So now we already know how to make alkynes, so what can we do with them, right? And you can see alkyne has 2 degrees of unsaturation. So we can put the hydrogen back in and saturate it. If you put 2 hydrogens, okay, that's hydrogen double bond, single bond. If you put 2 hydrogen back in with palladium as the catalyst for hydrogen to stick to, uh, 2 hydrogen molecules equal to 4 hydrogen atoms. So you put them all in, then the molecule become fully saturated. Okay, so that's the first one. That's the reductions. Reduction means adding hydrogens. Oxidation means adding oxygens, or reduction. um, Oxidation also means taking away hydrogen as well, but that's one way easier to think about oxygens as oxidations. Okay, now you can add 2 hydrogens if you want to fully saturate it, or you can just add 1 hydrogen molecules at a time. Okay, in the case of you go from triple bond to double bond, so you only add 1 hydrogen molecule, which is 2 hydrogen atoms. So that's going to be difficult, right? You have to control it. So the catalyst is it's called Poisson catalyst or Lindlar catalyst. So you have all kinds of stuff in here. You have hydrogen, palladium, barium sulfate, and quinoline. Okay, quinoline is very toxic. Okay, so it only happened once and it dies out. Okay, so that's why it doesn't go on. And remember, the product is always cis, because every time you have a catalyst, from my observations, it's always cis, because catalyst, the hydrogen stick to the catalyst only on one side. That's why. Okay, only one side, and then it bring that hydrogen to the triple bond. So that's why the 2 hydrogens atoms are added to the triple bond, so it become double. Okay, only one. The second way to do that, if you want trans, it's going to have to be different way. You don't use catalyst. In this case, you use ammonia with sodium that make electron. Okay, so the mechanism is different. You have sodium donate 1 electron, and the ammonia will solvate the electrons. Okay, so the electron basically floating around in ammonia molecules. So the electron will be added to the triple bond first, rearrange them into, so you got a radical and an anion on the same molecules. And obviously the anion look for hydrogens from an ammonia molecules, okay, to recycle the base, which is good. Okay, now it take the hydrogen, so it released the amine, a very strong base. Okay, so but anyway, another electron will be added to the other carbon, the radical, so that pairs it up into an anion. Now you got an anion, so it's going to be hungry for a hydrogen again, pick up the hydrogens. And remember, this one has to be opposite, because it's trying to stay away from electron clouds, so reduce the repulsions. So that's why you get trans. All right, so that's very interesting mechanism. So you can do, we got the power, we got the tool. We want the cis, we got it. It has to be Lindlar catalyst. Remember, Lindlar catalyst, and these are the components of Lindlar catalyst, or just sodium ammonia, and that's we make the trans. Okay, so that's good to remember that. Okay, because it's very specific. You have to use the right reagents for a specific compound that you want to synthesize or react. Okay, a product that you want to make. Okay, so that's pretty cool reactions, right? So far, 2 different reactions. It's all adding hydrogens, all reductions. Now we add. Okay, remember the triple bond is deficient in hydrogen, so we can add things to it. Okay, and we don't have to add just hydrogen. We can add other things like acid, like HCl, HBr, right? or even halogens, X2, like bromine. You can add one bromine, okay, and it's going to go either cis or trans. So you got a mixture of two products. If you add two bromine, of course, it's going to fill all up, right? Okay, and same for chlorines. Now, adding acid, HX, hydrogen halides, not acid, I'm sorry, hydrogen halide, it's going to be tricky because where does the hydrogen go? And where does the X go, right? And it's going to follow just like alkene, Markovnikov, right? So the hydrogen will be added to the terminal carbon or the carbon with more hydrogens and the terminal. So here the terminal has one hydrogen, so it's going to be added there. It's going to take up there because it's formed the more substituted cation, more substituted, or internal is more stable. All right. And then the Br minus will be added there. Okay. If you do it 2 times, they still go the same way. So they don't spread out. Okay. The hydrogens still go outside and the 2 Br go to the more substituted carbons. Okay. So the bottom line, if you do 1, then you can get, addition cis or trans, or if you got 2, the 2 Br it's going to be on the same carbons. All right. Now, you can also do anti-Markovnikov, just like alkene reaction with HX or HBr. You use radical mechanisms, and you get the anti-Markovnikov. So it go exactly the opposite. So the Br will go into the carbon that's less substituted, and the hydrogen will go into the carbon that's more substituted. Okay, and hydration is adding water. They follow Markovnikov, and we use oxy mercuration. We use mercury to, in this case, mercury sulfate to speed up the reactions. The purpose of mercury is also to prevent the rearrangements, because mercury is going to stick to the multiple bonds, right? And when you get rid of the mercury, it becomes a double bond alcohol. Now, you can keep going, but the double bond alcohol is called a eno, alkene alcohol. En for alkene, O for alcohol. And it will rearrange. We call that a tautomerizations. And you can see the double bond will take the hydrogens, and the bond between the oxygen and the hydrogen will become a double bond. And you end up with a ketone, which is more stable than 2 functional group, alcohol, alkene, combined. Okay, so ketone is more stable. And so that's addition of water. So when you add water to a triple bond, it becomes an eno and then become a ketone. Okay, or aldehyde, depends on where. Okay. The acid catalyzed, this can go by itself, or you can throw in a little bit of acid and it will rearrange into a ketone as well. All right. So, and then here's the overall reactions. When you take a triple bond alkyne, you add water. So mercury sulfate is just helper, and that's acid is also a helper. The main thing is the water. So you get ketone, all right, and you get 2 different positions. Either you get the double bond right here or right here. Okay, so equal chance. So that's why you get 2 different products. And they're both good. They're both major products. Just like alkene, notice this is very similar to alkene, except it's a triple bond. So we gotta think carefully. What's next, right? We can also do anti-Markovnikov. In this case, for alkene, we use BH3. And here we use a little bit more complicated dialkyl boron complex. Here is isoamyl, okay, with hydrogen peroxide, and the basic conditions, anti-Markovnikov. So guarantee, okay, the double bond's gonna go to the less substituted carbons. If it's terminal, it becomes an aldehyde. All right. So it's always a fixed product, which is really nice, if we want to make that particular products. Now, okay, so that's addition of water. Mechanical or anti-mechanical, your choice. It's just different reagent, and will get us there. Now, for oxidations, we can, like I said, oxidation, the easiest way to think about oxidation is to add oxygen to the molecules. Okay, so here what we're going to do, we put two, we saturate this guy, okay, with OH. So you got 4 OH everywhere. And of course, that's too many. So it has to eliminate, in each carbon, it's not stable to have 2 OH in each carbon. So it has to eliminate one. But obviously, OH cannot be by itself, so it's going to wrap the hydrogen with it. So that's why for each carbon, we eliminate water. For 2 carbon here, we eliminate 2 water. So you end up with diketone, which is a stable compound. Okay. So the overall reaction is going to be dilute neutral KOH, KMNO4. We got diketone. But if we heat it up, okay, it's going to break. Okay, you notice the difference here. One is neutral dilute. The other one is KMNO4 with a strong base, potassium hydroxide, and heat. So it will break. When it breaks, it's going to form carboxylic acid. But of course, this one is a strong basic condition. So it's KOH will rip off the hydrogen from the carboxylic acid, turn that into a carboxylate. And then if you want to get to carboxylic acid back, you just have to neutralize it with, or acidify it with HCl. Okay, and that's an easy step to get your carboxylic acid. So in this case, it's a two-step, 1, 2. It's 2 reactions. Okay, one after the other. You get the triple bond cut down into 2 carboxylic acid. Okay, remember that. All right. Now, if we combine those 2 together, it's going to be step 1. You see, that's step 1. You cannot do step 2 and 1 together. You have to do step 1 first, and then you do step 2, and then you get your 2 acid. But because this one is terminal, so it's carbon dioxide. Okay. Maybe a couple more, one more, and then we good. Which is the last one here, ozonolysis. Also, cleavage of the triple bond, cut the triple bond. Under neutral conditions, ozone, okay, cut the triple bond, and we get the carboxylic acid on both sides. Okay, so that's if we want to run under neutral conditions, and that make it easier. So here's the little puzzle for you. If you got the 2 products, now you're going backward. Okay, which compound, which alkyne would you pick to get these 2 products? Okay, so that's kind of thinking backward. It's kind of nice. Okay. We call that a retrosynthesis, going back and figure out what the reagent is. Okay. All right. So and remember, okay. So these are the really strong conditions, basic and then acidic. But here is ozone is nice. It's neutral. In case you don't want to use something acidic or basic. Okay. All right. So that's the. So it's not too bad. Maybe 3 or 4. 5 different reactions for alkynes. It's always good to make a summary of what we've been talking about, and do some practice question here. Okay. All right. Thank you for watching. Okay.